This meeting is being recorded.
So let's first talk about what this documentation is about. This is it's called a physically based rendering in Filament, which is a render by Google. And it looks really nice. And the good thing is that it provides this documentation about how it is implemented. So this documentation is a pretty good material to kind of learn how a PBR renderer is implemented. That's why we are looking at this documentation. So I think today our task is to finish till 4.6, but if at any point for any equation you don't understand, let's just discuss it. No need to rush to 4.6. So first, let's start overview. Filament is the PBR engine for Android. So for Android, that means it must be really power efficient and it can't do a lot of fancy things, but it's still PBR.
I guess part of that would be that they can't is like on mobile it's mostly bandwidth like capped, right? So I guess they don't want to be I guess like reading as many textures.
I honestly don't know.
The specifics of it, I'm sure, are described in the detail in the parts where they say we chose this because of Y reason. Mobile is power constrained. What I think that really means is they're saying we made sure to always be analyzing what algorithms we chose for performance, which is something that if you look at the path tracing PBR text and tutorials, they just kind of say, well, you're just going to be you're going to be Monte Carlo sampling. So the performance of each individual thing is kind of whatever. Whereas on mobile, it's way more important.
Yeah, but also like all the real world path tracing real world path tracer will cheat in various ways because performance of brute force path tracing is just not good enough.
Fair point.
Yeah,
absolutely true.
Yeah, it definitely is the case. I've been running just a brute force path tracer for about 6 days here.
6 days.
That's quite brute force.
It's generating like 8,000 outputs, but it's I don't know, dumb little project.
Yeah.
So explain the equations and theory behind the materials and lighting models. That's the purpose of this documentation. So prepare to see a lot of math. That's my take. And we will provide code snippet. This document is not intended as a design document. So more about algorithms, not about how to do software engineering kind of side of things, I guess.
More theory than implementation. Yeah.
Which is kind of what we want to see in this document.
So do you want me to read this section?
Yeah, sure.
Real-time rendering is an active area of research. So there's a lot of things to choose from and implementations for those things you choose. So we need to define our goals. It references or principles. Oh, okay. So the physically based shading paper at Disney, which itself is its own long piece of work. So the goal is real-time mobile performance with a target of OpenGL ES 3.x class GPUs. They'd prefer quality. They want high overall picture quality. They will accept compromises for low performance GPUs, however. They want it to be easy to use. So iterate often and quickly. Parameters need to be simple. Yeah, nothing that's fiddly or difficult to understand. Our system has a few parameters as possible, so that's nice. So it's not going to be something that's infinitely configurable. It's going to be, here's the basic parameters that you need, and that's it. And
also, any combination of parameter values should lead to feasibly plausible results.
Yeah, that's interesting.
Yeah, I don't know how they can achieve that though, but yeah, that's definitely interesting.
Yeah, so they try to do everything in the same unit system, meters, Kelvin, or a consistent physical unit for everything rather than arbitrary things. So they want abilities to include non-PBR materials in their render, and just make it small. Make the project small for things.
I guess for this documentation, those are more like the engineering side of things, and those are more like rendering side of things.
Do you want? Who wants to read the next section, or do we want to trade off, or what?
Yeah, I guess we don't need to read line by line, right?
Yeah, it's fair.
Yeah, it might be good to just skip the chapter 4, because I feel like this is better as a come back to it when you see.
Yeah, I guess.
Actually,
yeah, the notation.
This is just like a bunch of sentences about what PBR is.
I'm going to take a screenshot of this.
Yeah, this, because if we have equations, this thing will be useful. Let's actually do this.
Actually, yeah, just having a little floating window. Yeah, that would be nice.
Is that a? Oh, that's not. That's not an image. Darn.
You can just screenshot it or something.
Yeah, that's what I'm doing myself.
Wow, what happened?
Jesus.
Okay. Yeah, you open up a new tab.
Yeah.
Whoa.
Can you see my full screen? Or you can only see one tab?
I can see both.
I can see both. Yeah.
Nice. Yeah, but I don't know why this one doesn't render.
Might give that a refresh.
Go. Oh. There. It started working again.
Yep.
Okay.
So what happened? The sections below describe multiple material models to simplify the description of various surface features, such as anisotropy or the clear coat layer. In practice, however, some of these models are condensed into a single one. I think I need to read the later part to understand what's going on.
Yeah.
Any question of this part? I don't understand, but I think I need to read the later part.
I think they're like talking about like basically having different BRDF and BSDFs for like if they want anisotropic materials, which if I remember right, that's basically it can reflect differently depending on the direction the light's coming from.
Yeah, it's different direction.
I think it's pretty much just they have different roughness on different axes. So I think anisotropic, they have like 2 roughness value to control the roughness, but for the isotropic, they only have 1 roughness value.
So I feel like my interpretation of this is basically just talking about how you can combine like BXDFs. And
they're also cool to get like the clear coat layer, maybe to get some like thin film things on other material. That's kind of cool.
Yeah, I guess it's just like combine all those different layers into a like Uber material kind of with more parameters.
Kind of generalize it a bit, yeah.
So the standard model, BSDF is the generalized bidirectional scattering distribution function, which you can decompose into BRDF and BTDF. But they're doing BRDF primarily and ignoring BTDF or approximating it greatly. The second sentence in the second paragraph says, our standard model will therefore only be able to correctly mimic reflective, isotropic, dielectric, or conductive surfaces with short mean free paths. So that's kind of describing the surface types that they actually want to support with their standard model.
What are we meaning by short mean free paths?
I assume they mean the light does not bounce around on the inside much. It almost always is emitted close enough to where it was absorbed into the material, as in.
So I guess is the point is we can just kind of roughly see the entering point and the exiting point as the same point of every light.
Oh, so I mean, I don't know if this is common knowledge, but Wikipedia tells me a mean free path is the average distance over which a particle moves before it changes direction. So I guess this is basically saying conductive surfaces. So, there is some subsurface scattering, but it's all done in a very small area.
Yeah, exactly.
When I flicked through the paper before, I saw pictures for the microfacet stuff, which is in this section. And that is directly related to that kind of idea of expressing subsurface detail as a single parameter rather than as a physical calculation. So we got a diffuse component and a specular component.
Yeah, as quite familiar stuff.
Yeah.
So yeah, we have a diffuse component, and this is diffuse component and this specular component. And then we just need to add those two together. Yeah, we just add those two together.
Yeah, add the product or the add the specular and diffuse reflection components to determine our final brightness. Because it's an integration over a hemisphere. But so abstractly speaking, we can just add the two together. A microfacet BRDF.
The part that always confuses me is maybe they'll get to this later, but the adding together the diffuse and reflectance and how you make that energy preserving. Because I feel like I've seen it come up a lot where it's not necessarily always true that you can just add them together, because like you might be double counting some light, because like I thought the whole kind of PBR standpoint was almost that there is no difference between diffuse and diffuse and specular, because it's all like one model.
It's all in one BRDF, and this particular BRDF use diffuse and the specular separately.
Okay.
I think some BRDFs have a correction factor for that kind of stuff.
Yeah, because I thought like the whole microfacet thing was basically saying that like diffuse and specular aren't really different, and it's just like about how many of the microfacets line up to make it look diffuse or specular.
I guess like specular is still like light immediately get reflected, even though it's not exactly like a mirror because of those microfacets. And diffuse is like light have a little bit of subsurface scattering and then go out.
Yeah.
That's the idea.
The microfacet description is a large number of randomly aligned planar surface fragments, which means you'll get some amount of perfect reflection, but because the surfaces are randomly oriented, they'll be in a random direction, which isn't to say that all the light is going to be perfectly reflected off these randomly aligned surfaces. Some of it is going to be absorbed and scattered in a random direction, a diffuse, the diffuse component. And so it's almost a way to say that there's two things going on here, how reflective versus diffuse, how reflective or not the surface is, and how much the surface is bumpy. And we'll have the microfacets that reflect in random directions, as well as in adding to the diffuseness.
Okay. Yeah. I'll wait to see what they have. What the terms actually look like.
Some of the microfacets.
Normal is oriented halfway between the light direction and the view direction view. Yeah. Will reflect visible light. Like this surface will not reflect any light. Makes sense.
Yeah. And to continue on from that, if you scroll down, it even talks about shadowing and masking, where parts of the surface won't be visible thanks to the bumpy nature, and some of the light will just get blocked by other surfaces.
Yeah, I guess it is like the micro facet stuff is quite similar to the like larger stuff. We will need to consider this like kind of like Lambertian term is this it will be the distribution of those microfacet. And then we have this term for geometry shadowing stuff.
So it almost looks like the microfacet, how much microfaceting is going on will greatly influence how dispersed the reflection lobe is.
Yeah, that's what this roughness parameter is for.
Yeah, okay, and that's basically.
Yeah, it describes how smooth a surface is at a micro level.
Oh, we're not there yet.
So it's kind of how broadly distributed those, the micro surfaces in terms of, difference from the macro surface there.
Yeah.
Yeah.
In another word, it's like how polished the surface is. A polished surface is going to be nearly perfectly flat at a micro scale, whereas a rough surface is going to have a bunch of divots and gullies and peaks on the micro scale.
Yeah, exactly.
I probably wouldn't be wrong to say nanoscale because light is only 100, like 300 to 700 nanometers long, and that's the wavelength of the light of the radio waves. So the details of surface object, the surface details at the scale of a couple of hundred nanometers is important for the reflection, the behavior of the light.
But I guess this microfacet model don't really think about that.
Well,
Yeah.
okay.
It's more like at a sub-pixel level, not at a nanometer level.
We're not modeling at the nanometer level. We're not modeling geometry that detail. I'm saying it's an approximation for that level of geometric detail that we don't currently process because that'd be insane.
Yeah, I don't. Yeah, I'm not. Yeah, you're not getting a lot of like wavelength considerations. Yeah, so it's really it is on the micro scale rather than nanoscale, I think.
Oh, okay, I can see that. Yeah. Okay, maybe I'm overthinking things.
Yes. So the roughness parameter as set by user is called perceptual roughness. In the shaded snippets throughout this document, the variable is called roughness in the perceptual will be with a remapping explained in section 4.8. So we will not talk about it today, but I guess it will be some kind of curve. The microfacet model is described by the following equation. So this is actual BRDF with all those different terms.
I guess you have two of those, right? Because you have one for diffuse and one for specular. In this case, at least.
Yeah, it looks that way. Yeah.
Because they had they called it F subscript X, so you have to have one for each of them.
Where we are again? Oh, yeah, here.
There.
I found the Disney physically based rendering papers, so that might be useful to have to reference while we're reading through it. So we got, I mean, it might take a minute to
It's
find.
not a good time to read that though.
No, I'm just saying, it references the Disney thing a couple places, and it'd be good to just have it to find the paper because it's not actually linked in the sources. Okay, what's this equation?
Yeah, so we have the distribution of microfacet, normal distribution function.
Primordial is an interesting term to use there.
I actually don't even know what that means.
I guess I'm reading it like it's a kind of a primary role. I don't. Yeah.
Existing at or from the beginning of time.
It's like a basis for everything that follows. I guess.
The second definition, it says fundamental.
Okay, yeah, I see.
Hey, I have a question. This is not real time, is it? This is
It is real time.
It is, okay.
It is on Android.
Yeah.
Right. That's what I was confused with. Because it seems like a lot of calculations for real time.
PBR definitely
it's actually not that lot.
I think they derive more basic models from these equations.
PBR
since there's only one, if you have like direct lighting, there won't be too much lighting that you need to calculate. So probably only one direction that you have to calculate that.
Yeah.
Okay, thanks.
It's not like path tracing level calculation, or even just weighted style ray tracing level calculation. It's much less than that. G is the geometry term, I guess, for the visibility. And
yeah, so F of M or FM is the actual BRDF.
It's the actual BRDF for specular and diffuse.
Yeah, combined.
So I guess this is more of the, like this Fx is more the lighting equation.
Yes, it looks like f of x is it's trying to combine together the microfacet calculation, the visibility calculation, and the microfacet with the microfacet BRDF, which
they don't really do like the light power coming in though, do they? Or am I missing that?
They may not have gotten to that point yet.
I'm curious just what this equation
I think it's
represents.
still BRDF, but it's on a macro level, and this is like microfacet BRDF.
Oh, okay. So yeah, so it's the combined BRDF containing a couple of sub BRDFs.
Yeah, exactly.
Okay. Yeah, okay, that makes sense.
What is M? No, it's the internet, or
I think that just stands for microfacet. So it's like if you look at the picture, that the pink area, at the micro level, it's saying that's you're integrating over that hemisphere, over that area of micro surface, rather than it being a flat plane. You're having to consider the micro surface details and the.
I see. Yeah, it's being integrated.
I'm thinking could that be the normal of the microfacet? I think maybe the D like the.
I guess it's normal.
That must be the normal because it's a vector, right?
Yeah.
Yeah.
They should list that in the symbols.
Yeah, in there they don't have microfacet in that symbols. Maybe you just like introduce a microfacet theory and then maybe just ditch that and continue to the BRDF.
Wait, it's not the normal, is it? I think it's. Oh, sorry. Yeah, of the current microfacet.
Yeah, because it's a whole bunch of different it's not a flat surface. It's a whole bunch of different surfaces next to each other.
Oh, so you're integrating over every possible orientation of the normal, and then plugging that into like the G to get the shadowing of that specific normal.
I think it's like actually integrate inside that area. So the area could contain a bunch of microfacet, and it's like the distribution of the D function is like how giving a normal and the roughness, they're gonna tell like how much of those microfacet are facing the direction of M.
Yeah. Okay, that makes a lot of sense.
Also, it assumes all the incoming rays are parallel, which is nice. Apparently, if you the last paragraph of this section says it is obviously not practical to impute the full integration over the microfacet's hemisphere for each shaded fragment. We will therefore be relying on approximations of the integration for both the specular and diffuse components. So I think it's just trying to say that we're going to be doing a lot of approximating for the microfacet surface calculations, rather than brute forcing a integration.
Yeah, we don't want to a lot of like doing loops for each individual pixels to do integration. So,
okay.
Dielectrics and conductors. Yeah, this is This is what I was talking about. Part of the light will be scattered inside the surface, and part of light will just reflect immediately.
Yeah, that makes sense. Okay.
So it further delineates that there is no subsurface scattering with purely metallic materials.
Yeah,
meaning
yeah.
there is no diffuse. Scattering happens in dielectrics, though, which means that they need to distinguish between dielectrics and conductors or metallic things.
Seems reasonable.
That's how usually in like real this kind of BRDF, they will actually have a metallic term to you can make a material kind of more like metal or less like metal.
I think in this one it's like a Boolean, right? It's like 0, 1, and you can do it in a texture map.
Yeah, in here is a Boolean, but then if we provide a metallic term, it can be more flexible. Right?
Another interesting piece of vocabulary, modelize.
Yeah.
I said some sort of math jargon, and my mom was like, "That's not a word." And I'm like, "It's a math word. Of course you don't know of it. You don't do math stuff. You don't like it." She's like, "Sure." And then so I looked it up, and like the second definition on wiki whatever was the math term.
What was it? What was the term?
I forget. It's like it's one of those things where you like algorithm and algorithmarize or something where you turn it into a verb, something like that. It wasn't
I'm
that.
pretty sure everyone knows algorithm, the word, even though they don't know what that means.
Right, but the thing I said was like to algorithmically determine the something, and that's what was confusing to her because it was used in like a verb rather than as a noun.
Okay,
anyways.
Some less than mainstream usage.
Yep. Got energy conservation, which is a big thing in PBR. I mean, the light out is
the
equal
total
to or
amount
less than.
of the reflectance energy is less than the total amount of incidence energy. Otherwise, we just have more light. When we have more bonds, it totally doesn't make sense.
That says less than, not less than or equal to, which is something I've seen described before, because a perfect reflector would not absorb any light. Unfortunately, perfect reflectors basically don't exist. So
it doesn't matter.
Yeah.
Also, wouldn't you like not be able to see it? I guess it would just be a mirror. Yeah, right.
Yeah. It'd just be a mirror that does not absorb any heat from the light that's incoming at it.
Yes.
Yeah. Perfect for surface mirror, I guess. Yeah, because because then if it was I guess you'd have to think about like a clear coat. I guess they talk about that later.
It can also be a diffuse material if it does not absorb any light.
Yeah.
But I guess it just doesn't make that much a difference. As long as it's less than or equal to this, equal really doesn't make much difference with like slightly less than.
I know one of the tests they do for energy conservation is that that like furnace test where it's a ball inside of an all white box, and you look at how it reflects there. Yeah, I have to look it up.
It's supposed to be like pure white, right? If it passes.
I think that's right.
Yeah. Can be modeled. The Micro BRDF can be modeled with the Fresnel law. Everyone know what Fresnel is? Or
it's not
should we talk
pronounced
about it?
Fresnel.
I think I pronounced it correctly, but
Oh yeah, you did. Yeah.
Yeah,
I did not for the longest time.
Same.
I think they talk about it in a like down a little bit more. Yeah, 4.43 is the Fresnel part.
yeah, I guess this is a good picture of what Fresnel phenomena is. So you can see here, you can see underwater, but at here you can just you just can't see what is underwater, but you can see the reflection
You
much
reflect more
stronger.
gray signals.
Yeah, exactly.
Okay, so this is just the exact same equation as before, except Fm got replaced by the Fresnel.
Yeah, but it's already an approximation. It's the covariance approximation because we don't have integration anymore.
Right. Yeah. Okay. Yeah. So they've already simplified it, but it's replacing that same equation.
Yeah, it's replacing that with this Fresnel term basically.
Yeah. Oh, so is that VH F0 over 4 n dot V times n dot L? Is that the Fresnel term?
I think just
No,
the
just the big F is the Fresnel term.
Oh,
like
okay.
in the previous integral one, that's
Yeah.
the Fm, and then you can see in the previous equation that first multiplied by 1 over n dot V n dot L. So that's just that part.
Oh
I'm
yeah.
not sure why they have. I guess that's the Cook torrents is adding the 4 in there.
Yeah. Also, I just want to point out the H, which just kind of appears, is just the half unit vector between L and V. So it's halfway between the view vector and the light vector, the incoming and outgoing light directions, kind of. Or
It's
the
like-
viewing,
Yeah.
It's like Fong is.
yeah. And so it just uses that in places as a so he doesn't have to provide the L and L and V directly and have them compute it. And the A is the roughness coefficient, or it's an input parameter for the material. So passing A into D and G just makes sense because they are the microsurface stuff. The what did I write down? The distribution and the visibility and occlusions terms.
Normal distribution.
Yeah, NDF.
D.
Is that the alpha you're talking about, the A?
Yeah.
Alpha,
Yeah.
Okay.
the roughness.
Yeah. I just saw those and was like, where'd they come from? And it's like, yes, they're going to be the same across the material. The A is
Surface
at least.
parameter, yeah.
Well, not the same, but it's going to be dependent on like if you're if you're sampled a texture to sample the roughness, but yeah, it's an input of the material, not of the current pixel being sampled. Well, I guess it depends on the pixel being sampled. Anyways, okay. It's a normal distribution function.
I guess the GG and GGX stands for ground glass. It's supposed to be like that kind of reference. I think I remember reading that at some point. Could be making that up.
It's interesting they say it's equivalent to the Trowbridge-Wright's distribution. Not like, does that mean it's the exact same or like?
I don't understand how this comes from. You don't have any explanation of that. Because this Burley paper.
I see people like I just searched online. I see people say like GGX / Trowbridge, right? So I think it really is just the same name, different name for the same thing.
I wonder if they just got this by curve fitting.
Yeah, so maybe it's this is an approximation to the actual Trowbridge rights distribution or something.
Yeah, this is approximation. Of course, it's an approximation, but yes, I don't understand how this comes from. But
I think they usually just say that's. Yeah, I think that's usually just kind of like above our pay grade.
Yeah, I guess there are more materials. So if we want to read them, then we can understand more. But otherwise, we just see, hey, this looks pretty good. So let's just use this. It's a long tail normal distribution function. So I guess it's a normal distribution based on the roughness. Is this roughness?
Yes, it's roughness.
Let me check it's roughness or roughness square.
Oh, they have it on your left screen.
Yeah.
The little definitions thing.
And it also,
I just checked what his actual normal distribution looks like.
This is not that normal distribution. That's the distribution of the normal vector. That's very confusing.
So is it a normal distribution?
No, it's a distribution of the normal vector.
Bad joke. That was a very bad joke I just made.
Abnormal normal distribution.
Is there ever a moment in this where they ever use like the normal distribution? Because I don't think so, right? So I think you can just always take it as the distribution of the normal, right?
Wait, is it saying that
some very bad wording?
A long-tailed normal distribution function is a good fit for real-world surfaces? Is it saying that a normal distribution is a good fit for normals of surfaces?
A long-tailed distribution of normals.
No, I think early 12 is saying the first sentence.
Well, it's saying the normal distribution function. So the distribution of normals is long-tailed.
Let's check that paper. Maybe they incorporated some normal distribution to fit that function from some database.
I think they're just describing GGX as long-tailed. Like
any.
Oh, that's.
That looks like normal distribution.
Because they always they say NDF, right? They previously described NDF as the distribution of the normals. So they're observing that a long-tailed normal vector distribution function is a good fit.
Okay, I guess I need to read this later. We can improve this implementation by using half precision floats.
Yeah, because it's a direction. It's not a distance. So they don't need the utmost of precision.
Isn't it the case that not everything supports half precision floats? Is that true?
I don't know.
I feel like on desktop hardware, I feel like I've heard that that's not always guaranteed, but
I thought it was pretty much universally supported, but
okay, I would believe your
there's a difference between there's a difference between half precision storage and half precision computation, and they need to distinguish which one they're referring to, because for a bandwidth perspective, if you know that the output you store doesn't need you don't need to have all the precision in the stored value. That's great. But if you're talking about, well, this intermediate step doesn't need full precision either, then you'll have your, you'll want to do the math in a half precision calculation mode, whatever that means.
I think they are talking about half precision correlation in here.
That's good.
I know 10 and 11-bit floats are pretty common for real-time stuff.
Yeah. For storing colors and whatnot.
Yeah.
You do have to be leery of your math when you do have half precision, though, because half as precise.
Yeah, maybe some quantization.
Not half precise. It's way worse. Right.
Yeah.
I guess multiplication can easily blow it out, right?
Yeah, they're saying when NaH are close to each other. What is it?
When it's close to 1, then
when n times h squared is close to 1.
Or n dot
Yeah.
h, right?
Product,
yeah, sorry, dot, not times.
I have heard this referred to as catastrophic cancellation.
Me too.
Yeah.
When all the precision dies because you're multiplying two very small numbers or two very large numbers, not large, but you're subtracting two things that are very close together, and then there goes all your precision.
And then you get 0 and boom.
I've had to deal with floating point turning into nan, and it might have been due to this kind of thing.
Yeah.
Lagrange's identity, is that just the square of the cross product is the square of the normal of the two terms minus the square of the dot of the two terms?
Yeah.
The two terms squared multiplied minus the square of the dot of the two terms. What?
Oh, so they just use the cross product to avoid the cancellation. Like they just don't do n dot h squared, they do n cross h squared.
Circumvent the issue.
Yeah. And if they're already unit vectors, then the magnitude of A and magnitude of B are 1. So that cancels out and turns into 1 minus n dot h squared.
Unit vectors make everything easier.
Just got to make sure they're unit vectors to begin with.
I'm sorry, I have a dumb question. The cross product on the left side, the a times b squared, or axb squared, that returns a vector, right? But on the right, it's all scalars. So how does that work?
This is a scalar.
It's a scalar. It's a scalar because it has the.
It's a norm
it's a magnitude.
of the cross product.
The bars.
Oh, it's the magnitude. Okay.
Yeah, right.
Yeah.
I got it. Thank you.
But that interesting that's you have to like do the cross product and then normalize it and then square it. I feel like that's gonna be a decent amount of like operations, but I guess that's still better
No,
than
actually it's just cross and dot, right?
Yeah, it's not normalizing
the dot is just cross and then they do dot.
Okay.
They're getting the magnitude. They're not normalizing the vector.
Right. Yeah.
Okay.
Shadowing. I guess this shadowing term can be split into the incoming and outgoing, and then just multiply them together. That makes sense.
G is our visibility and occlusion aspect. So
Yep.
rather, so the 4.4.1 is all about how distributed the roughness turns the light rays, how much scattering, scattering the microfacets do, and then the geometric shadowing is to how much of that scattered light is blocked.
Yeah, exactly.
So like specifically.
So this is like shading in the micro level, and this is like shadow in the macro level. Even though because they are in the macro level, when in the bigger scale they all become shading.
Yeah.
So just to clarify, in the last one, the D is that function is basically for the D term that's representing, given a normal vector, how likely is it in this distribution?
Yeah.
Okay.
Yeah.
Also,
well, I thought the D term was the basically the approximation of the integration over the surface for D.
It's just one term.
Yeah, so now you're just using the half vector.
They don't have any explanation of how those things get. Like, what is this?
A couple things in this paper are a little hand wavy.
It says from X source, there's some things we got, and I bet the source might lead us to the answer.
Yeah, that GGX paper I linked seems to have all of this in it. So.
Okay. Good.
But I guess this is more like a description of what they did. It's not course on how to be a master in PBR theories.
I guess to be fair, like the G and the D are both basically just like distribution functions, right? So
right.
So like it doesn't maybe matter how they came up with it, just that the shape of it looks right.
Yeah, but I feel like there must be something in it, but
because I like the filament just because it does show the code eventually. Like we have all these equations. What did we write the code to match these, to implement these equations with?
Yeah. This is like an interpolation with roughness.
I'm interesting that they combined the geometric shadowing term with the for n dot b n dot l. So like the macro. It's interesting that they combine that.
Yeah, this is just some cancellation stuff. But I'm still thinking about how this works.
Oh,
wait a minute. I'm still thinking about how this works. So when the roughness is small, when roughness is 0, we get n dot v. So we get n dot v plus n dot v. So we get 2 n dot v. So we get 1.
Yeah. So
when roughness is small, we always get 1.
Yeah, we got 1.
When the roughness is large,
just made it become smaller.
Yeah,
I think the function is pretty much just to describe how much of the light has been blocked by the shadowing and masking. So so at the end, so if we got rougher surface, we got more light being masked and shadowed. So we got less light coming out from the surface. Yeah, I think I saw the on the real-time rendering book. It had introduced multiple method to incorporate those two shadowing and masking function. I think this is probably the simplest form that we just multiply them together. I think there's something that you can weight between those two. Yeah, so yeah, they're just approximation, and none of them are 100% accurate.
Yeah, it's a pretty simple approximation.
Yeah, just multiply.
Also, with this approximation, it's very easy because we have those two terms which can be cancelled with this. So,
okay.
Pretty nice. That's how we get this V, which is by our original geometry term G divided by this term, which can be cancelled. What is this masking? I'll check it later.
Oh, that unity guy.
It's the derivations. It's how these formulas came about. So it's very detail oriented.
So taking the height of microfacets into account to correlate masking and generate a little more accurate results.
So that's the heaviest.
Yeah, I don't even know how to pronounce this.
Is that a chi?
Maybe. It's basically a step function.
Hi.
Yeah, okay. So that's just 1 if greater than 0.
Yeah, 0 otherwise.
Okay, so that just protects you from having negative. That's just like a absolute value kind of, isn't it?
Yeah.
Yeah.
It's one of those things that math purists would argue is like, that's not a real math function. It's like, well, yeah, it's discontinuous. So
the real world is discontinuous.
Yep. Yeah, or the counter argument is like, but the absolute value function is discontinuous, and yet we use it all the time. Why is that one special? But
yeah.
So there's that delta function that you use in electrical engineering where they it's just a spike at 0 and the integral is 1.
Oh, is that the like Dirac delta or something?
Yeah.
There are a lot of different delta functions. All of them are discontinuous and have really weird properties.
In this, I'd be interested in how this is height correlated with all the like, I guess, with all the like cosine and tan.
What's the delta thing on the denominator that you just highlighted?
The upside down V.
Is that a lambda?
Yeah.
It's
lambda, I think.
This
uppercase lambda.
Yeah, I think so.
Oh, this is lambda.
Lambda.
I thought it's delta. Okay, it's uppercase lambda.
Oh, uppercase lambda. Yeah.
Okay. Okay, and lambda is this.
So that's somehow relating the roughness into the height of the microfacets. Like, I'm curious how that works.
Because they have this. What is data there? We just.
Oh, is that oh wait, theta m. So that's probably the angle of the vector, like of the angle from the surface.
Yeah. So how non-planar is the microfacet plane?
Yeah, the cosine of theta m is n dot v.
Did it just get rid of all of that because the cosine stuff? Oh yeah, because it turned the tan squared into 1 over cosine squared. And then it's saying, oh,
Yep.
but we can replace the cosine of the theta m by n dot v somehow.
Yeah, so we get rid of tricks, which is always nice.
Well, so they pass in v to this lambda and they pass in L separately. So why can they just replace cosine theta m with n dot v?
Well, I know cosine of an angle is equal to the dot of the two vectors is a common identity.
I guess this is just some bit of ambiguities because it's actually n dot v here and n dot l here.
But like if you look at the G where they use this lambda, they pass in v and then they also have a lambda of L. And that angle is related to that vector, right? So it's the angle of v and then separately the angle of L, but they replace both with n dot v?
No, I guess it's replace this one's this with n dot v and this one's this with n dot l.
Oh yeah, you can see that down there. Okay, that's kind of confusing.
Yes.
Yeah, the wording is a bit confusing.
Okay, that makes sense.
And then we got this surprisingly simple functions.
Yeah. So you have the GGXB and GGXL term, which is the same thing, same formula, just with different inputs, the NOV or NOL, normalized view, normalized light. Yeah, incident light unit vector. And then, it just kind of, equation 15 is what the code is doing.
I want to ask a really dumb question. What is GGX?
I was trying to figure that out. I was trying to look at the paper and I didn't quite get what the letters stand for. Did someone post this paper already? I don't know. It seems to be where it just says, this is our new model we call GGX, and it doesn't say why.
For some reason, I'm remembering that it stood for ground glass, but I really don't remember where I read that.
Maybe that's a backronym.
Could be.
Yeah.
It says GGX is a closer match for some of our surfaces than the standard Beckman distribution function, which I think is a complicated surface description function, but I don't know.
Could be people's names, something, I don't know.
Bruce Walter, Stephen Marshner, Hong Song Lee, and Kenneth Torrance. None of those letters make sense for that.
No.
We can optimize this function by using approximation. Now to notice that all the terms on the square root are squares, and that all the terms are in the 0 to 1 range. That's also a nice thing with square root, and then if everything is greater than 0, we can greatly simplify stuff.
Oh wow, so they just remove all the squares.
And square root.
Yeah, but that's very, they're not wrong, function. And that's very much not how it works.
It's a cool function because it's not square.
They know they know more. So
Yeah.
So they can do this only because they know more. So I think it's
good enough approximation.
Yeah, I just find that kind of funny that they just remove all the squares without doing anything else.
yeah. So it makes sense.
Yeah,
So
kind of makes sense. People won't even notice that because as long as they're in the range of 0 to 1.
That's an impressive short amount of operations for what the initial equation looked like.
Yeah.
Yeah. I guess it's just the same kind of thing.
It's looking at the GGX paper, they're talking about taking quantitative measurements of glass. So maybe could be related. I don't know.
Yeah.
Yeah.
Surface scattering like this is something you can totally do physical measurements, because you could just see how much light gets reflected at different angles around the hemisphere based off different surfaces you have, rather than color being kind of one of those perceptual things. Just the pure amount of energy.
Yeah, that's why we need like true mapping at the end. That's the only step we change from that light intensity into actual color.
Yep.
Okay, for now.
To summarize that section, there's a whole lot of math that you can distill down into a function which does the microfaceting we want.
Yeah. Yeah. For now, should we explain that, or does everyone know what Fresnel is so we can skip?
I Googled it. I kind of know what it is.
It's basically just like the angle affects how reflective it is, right?
Yeah, it's just a reflectance is greater at grazing angle. And it's much less when at instance angle.
I guess it's probably worth pointing out those terms F0 and F90 that they have right above the image.
Yeah, this is like approximation. Yeah, F0 and F90, you can see is the reflectance at the normal incidence at grazing angle.
Right, so F0 is looking straight down, so probably very little reflectance, and then F90 is completely flat, which I guess you can never really reach exactly 90, right? But
you can reach really close.
The limit of approaches 90.
Is the Fresnel effect that's being described on solid opaque surfaces the same thing that makes water, the transition from a media of different indexes of refraction have the lensing effect that it does? Is that what it's saying? And how you can not see into a surface when because fiber optics work by bouncing light at such a grazing angle that it perfectly reflects rather than passes through. But I've always associated that with okay, I have two media of different indexes of refraction, but is the concept of the Fresnel effect being applied to solid objects that don't transmit light at all, or very, very little?
That's not Fresnel. That's a different thing.
I was thinking about when you get the sort of the illusion off of like hot asphalt. When you look
I forgot what that is called, but that's definitely not Fresnel. It's a different thing.
Fresnel is essentially how much of the energy is bounced off versus goes in, right? So I guess once you're talking about the energy that does go in, then you have to calculate separately how the angle it gets slowed down at and everything, right, for refraction. But it's basically the Fresnel is about how much of the light got to that stage of going in, right?
Yeah.
So total internal reflection is a specific thing regarding light, but I was more
total internal reflection.
But I was more describing the fact that if you have water and air, they have two different internal reflection angles, or IORs, I should say, and that depending on the viewing angle of the light passing through the through the media change, it changes how the angle of direction and the intensity of it. And I'm just basically trying to connect that to the Fresnel effect. And if it's the same, it seems like the both total internal reflection and the Fresnel effect were studied by Fresnel, because he was the guy who studied this stuff in detail.
Yeah, I guess so. Yeah, it's different phenomenon because total internal reflection is more about refraction can't happen at that point.
Yeah, okay, that makes sense. So I have a Wikipedia article to read, the Fresnel effect, because I'm fuzzy on it. I get what's happening, or the consequence of what it does, but why it happens, it's mystical.
I guess I also don't know why it's happened.
More formally, below the figure 10, more formally, the Fresnel term defines how light reflects and refracts at the interface between two different media, or the ratio of reflected and transmitted energy, which totally has to do with the total internal reflection. It's just we're not in the world where total internal reflection occurs, because we're looking at solid objects, not well, some of the time we're looking at solid objects.
It's the same thing though, right? Because it's just
I'm basically connecting.
Okay, I guess so. I guess it's the same thing then.
I mean, I don't know if you'd use the Schlick approximation for total internal reflection stuff, but
I guess total internal reflection is not actually. Yeah, it's total internal reflection doesn't mean the material do not absorb something. It's more like refraction can't happen.
Yeah.
So I guess it's still different, but it's describing the same kind of stuff. It's just
sorry, I sidetracked the conversation a bit.
I messed around with this a little bit, and I don't have a super great understanding of it, but let me share one of these renders here. I did a path tracer that used the Schlick approximation, and it did do some total internal reflection stuff.
Yeah. In the Peter Shirley's book, we all did that. Let me find my path tracer. Okay, I gave up. Project is so lame, I can't even find it on GitHub.
Oh yeah. FYI, the Schlick approximation was the thing that gave me NANS. The power of 1 minus u to the 5th power. I had to guard that against NANS in when I was trying to do PBR years ago.
I did get some weird artifacts, and I think that's probably why when I was messing with this,
And it was very annoying to debug because I didn't know how to debug shaders at the time. I had set the output to an intermediate value, and it was very tedious and slow.
I guess when that U approaches 1, and they have a really small number to the power 5.
And then POW to the 5th. I mean, how does the power work in the hardware? I don't know, and it probably is a degenerate case. 0 to the 5th power. It should be 0, but it isn't. Maybe you got below 0. I don't know. I'm trying to remember things from many summers ago. Yeah. Observation of real-world materials show that both dielectrics and conductors exhibit achromatic specular reflectance at grazing angles. And that the Fresnel reflectance is 1 at 90 degrees. So at extreme grazing angles.
Why is the F90 afloat, but F0 is a back?
I guess just because you can have different reflectance for different wavelengths. That's how materials have color, right?
But when you're looking straight at it, you can. I guess that's the difference between metals and.
As grazing light, I think at grazing angle, yeah, at least for non-metal, you can always approximate it with white.
The paragraph right before there, it says it's achromatic for dielectrics and chromatic for metals, so it may be like color component.
Oh yeah.
I guess like why is F90 never chromatic?
Yeah,
that's just physics.
Interesting.
Yeah, I guess that's definitely beyond territory of what we are talking about, and we need to know much more to know why it's the case.
Oh, okay. Actually, they just make it a vector in the function. I didn't notice that.
Yeah, I see. Yeah.
So it is a vector.
They
They just make it. Okay.
Okay, they just act like it's a perfect mirror on all
Yeah, I guess it's just always going to be a chromatic, so they don't bother making a vector beforehand.
Yeah.
Yep.
So I was thinking, like, I saw them subtracting them, but that didn't make any sense.
Oh, yeah.
Good point.
So we start combining the things we just covered the specular BRDF. Now we're doing the diffuse one.
Yeah, exactly.
The spline branching function in the diffuse term becomes is it simpler than it should be simpler.
And
yeah.
we can use a simple Lambertian BRDF.
Yeah,
of course. So we don't even need to look at that. This is enough.
Yeah. The diffuse reflectance over pi.
Yeah.
It's literally 1 over pi times the diffuse color.
Yeah.
Yeah. Oh, yeah. Ideally, you want the diffuse part to be ideally coherent with a specular term and take it into account surface roughness.
Yeah, so ideally we can use something like that, but they said ideally, but it's for completeness. So I guess they actually just use this one for filament.
Yeah. I did try out the Disney one and like had a little comparison with them, and it did look slightly better. I will say that.
What? Oh yeah, I guess at grazing angles there are some differences.
It's not energy conserving. It says that in the next paragraph. The Disney one isn't.
Yeah, it's just
expressed here.
Just artistically looks better, I guess.
Yeah, like if you look at the very top edge of the right one, you can see it's like lighter, which I feel like.
Oh yeah.
Nice.
At that F90 angle, or near it off.
The delineation between light and shadow is a little sharper too. I'm not sure what that's about.
True, it's almost slightly more tuned looking, but it does work well, like realistic stuff.
Yeah, I guess it's more cartoonish. For Disney it makes sense because they do cartoon stuff. standard model summary.
Yeah, that's all the code that we need for our standard model. It's just less than 100 lines, less than 50 lines.
Surprisingly short.
So this is not actually a lot of calculation. Of course, we need to do an integration on this BRDF, but this BRDF itself is not a lot.
Yeah.
Well, we don't actually have to, though, do we? Because it's.
I mean, this is for a single
angles.
This is given a light direction, a single light direction. What is the material's color?
Yeah, so we don't need to do any. Well, I guess we would have to do integration if we wanted global illumination, but
yeah,
that's
the catch with all this like discussion of PBR in real-time rendering. The thing I didn't realize at first is that because we only do one light calculation at a time and we have limited numbers of lights, and shadowing, global large-scale shadowing, not microfacet, is really expensive, and indirect bounces are expensive. The PBR, it looks better, but it's because the lack of global illumination, it still looks very fake at times, you know.
Yeah, in this one they use image-based lighting, right?
I don't know.
I think so.
Let me look at the table of contents.
I don't know.
Yeah, they have image-based lights.
Okay, so that helps
much later on. But
I guess if we don't restrict to Android, we can actually do some global illumination later if we want to add to this, right?
Yeah. I mean, yeah, that sounds right. So we got our, just a quick summary. We got our GGX function, the F-Schlick approximation. We have our correlated GGX with Smith for our visibility. Is that visibility? Yeah, the visibility stuff.
Yeah.
And then we combine all those things together after calculating the normalized view, normalized light, normalized half of the view and light, and all those various things. And also the roughness is squared, which I find interesting. So the value you actually put in is going to be different than what's used in the calculation. It's going to be squared. So
that's interesting.
I think that's because the if you did it with a linear value, you would get all the the difference between 0.1 and 0.2 would be everything, and the difference between 0.3 and 0.9 it's all the same. And so by squaring it, the linear value makes more the value you put in as an artist. It's more of a linear response between 0 and 1.
Yeah,
it's the same kind of thing as like the gamma value, I guess. It's just
it is very similar.
Just for human perception.
Yeah, I'd say it's very similar to how audio is like sometimes incorrectly handled, where the volume difference between two audio levels is the perceptive difference between loud and soft is not the same as the linear amount of energy difference.
Yeah.
Because it's logarithmic. Anyways, should we stop here?
I just want to point out, I feel justified because I looked at 4.7.1, and my question earlier is a to-do.
Let's go to the GitHub page and start making issues about it.
Feel a little bit better about my question.
Yeah, let's stop it here.
Got through what we were hoping to. Woo!
Yeah.